Hello everyone, my name is Zapata Carratalá. I am currently a lecturer at the University of Edinburgh and an associate at Wolfram Research. I am also the president and founder of the Society for Multidisciplinary and Fundamental Research, SEMF. And I'm here to talk to you about the boundaries of language. The reason why I decided to give this short talk was that I'm currently working on a generalization of mathematical models that apply to biology, cognitive science, etc. And I wanted to give you a sense of what kind of trouble one runs into when trying to think of hierarchy structures in mathematics and science. So for that, I will use examples from other fields like music, but bear with me and let's get going. So the first thing I want to do is I want to simply summarize the phenomenon of communication as a natural phenomenon. So imagine that we're diving in the sea, we see an octopus that has some shells, and we can imagine that it will generate, if we see the numerosity of the shells is 3, there's 3 objects, we can imagine the octopus will generate some sort of concept of 3. This is of course reinforced by the fact that the octopus could also, for example, see and use a visual medium instead of a tactile medium to perceive the shells, and the idea of 3 will be somehow reinforced. So the key idea here is that these shells can then imprint a similar stimulus on another octopus, and that octopus will likely generate a similar idea or concept. Whatever that means in this context, we're just assuming these are very similar systems. They are very similar animals, and so it is likely they will generate that. So the focus here now is on the 3 shells, right? The 3 shells without the 2 octopus don't really carry any information, but when the octopuses are around, they then become sort of a vehicle for communication potentially. So this is the sort of phenomena that I want to look at, and I simply want to give an exploration and a rough classification of different communication paradigms or media. And for that, I want to think of these media or these objects or manifestations as expressions of the mind, very much in the sense of extended mind. So for example, we can start with cognophonies, which would be the expressions of the mind or communication via sound or vibration, so anything like whale calls or any biological rhythms like in heartbeat, or indeed something like the hypothetical perception of sound by plants, which is being researched at the moment, could be examples of this. Another would be shape, so cognomorphy, so the mind expressed as shape by direct interaction, be it by tools or in just building some objects around the beings themselves. And then of course, and perhaps the most important for us, is the expression of mind in space. So this is where the animal or the system is creating a distribution in space that carries somehow information and could be a medium for communication in general. So we are of course interested in human cognotopies in this sense. So cognotopy is a very broad term. We could be thinking of maybe cognography in particular if we want to think of sort of flat written patterns and things like that. But anyway, history has a very long list of examples of things that we could call cognotopies, and indeed things that interest us, which are symbolic systems that can convey information in a very deliberate and systematic way. So, of course, all written languages, all spoken languages for that matter, all kinds of artistic manifestations, all kinds of tools and devices that have been created throughout history and prehistory are examples of this. So these is in this large context of phenomena that I want to sort of frame my exploration. Again, my exploration is going to focus on 3 very specific ones, those being mathematics, music, and measurement in science, sort of the preamble to science, when we're just doing the measurement out in the world. So we'll go one by one, and I'll just basically chart a little bit what I think are some of the boundaries of those media, simply as communication devices, simply as symbolic devices. So let's begin with mathematical innovation. So this is a note on how mathematical notation can drive mathematical innovation. So let's first think about what kind of mathematical notation we've inherited from the origins of the fields. So this is some medieval copy of the Elements by Euclid. And we can see that the vast majority of it is text, is written language, and diagrams are quite literally side notes on the text. And then, of course, we have much later, we have something like logic. So this is an excerpt from Boole's The Laws of Thought, and we see a syllogism. And of course, we're all familiar with this now, but again, it is mostly text-based and sort of flows in a natural sequential way for the notion of logic and the notion of argument. So this means that we've inherited a wealth of sequential or binary notations and structures that we basically build most of our mathematics with nowadays. So you can see that all these notations on the screen are in some sense binary or at least sequential, and they have this sort of implied sequentiality about them. And so when we say sequentiality, we really mean that we're sort of following a trace on a single path, and there's no real notion of shape, at least not in a direct way. So more recently, diagrammatic languages have been developed. So the jump from a merely informative diagram to a diagrammatic language basically is the jump between a figure that is to be taken on its own and as an atomic piece of information, or one that can be fit into a framework and be composed and be exploited just like we exploit symbols when we build natural languages. So, for example, we have categorical or diagrammatic categorical calculus in which compositions, multiplications, symmetries, units, etc. are expressed in 2D diagrams, exploiting what is another example of a diagrammatic language, which is a knot theory notation, which allows to encode things like braidings, things that are three-dimensional topologies in a two-dimensional notation. And what's crucial here is that these symbols can be manipulated and be operated with just like we do with conventional sort of sequential notation. And of course, there's another example which is familiar to mathematical physicists, that is Penrose tensor notation. Now, these are good examples of pushing the boundaries of language, and they are by no means very extended and widely used. There are many projects that involve teaching these languages to young students much before they see the subjects that these notations came from. And there's good evidence that these notations are very intuitive and in fact are effective ways to capture at least some aspects of the mathematics that are being taught at higher levels. But ultimately, there are still phenomena, and this is where my current research comes in, where these notations are all still limited in capturing the basic conceptual foundations of the objects that we're dealing with. So, for example, in the context of ternary relations, these are relations between three objects, there's a natural way in which you can compose ternary relations. Very much in the same way that one composes binary relations by concatenation, one composes ternary relations by these three patterns of conjugation, in some sense, of combination in some way. So there are three natural combinations or compositions of ternary relations, and they correspond to geometries that are represented by those triangle patterns. These are combinations of three triangles, and those geometries are all part of the same phenomenon. So even in a two-dimensional notation, which is a stretch for current mathematical notation, this will be very limited because we have shapes that do not fit well if they are to be represented simultaneously on a two-dimensional surface. So 3 dimensions is possibly also limited for all the combinations that can be done of this, but certainly 2 dimensions is already limited. So this is an example of where 2-dimensional diagrams are still quite limited. And perhaps virtual reality will be a good place to start notating this sort of mathematics. And the ternary world and the higher arity world in general is full with this sort of phenomena. And examples are, for for example, what we are calling cubices for cubic matrices, which are 3 by 3 by 3 arrays of scalars. I mean, in the analogy of 3 by 3 matrices, these are 3 by 3 by 3 cubices, like a little Rubik's cube of scalars. And in the context of those objects, these sort of structures pop up naturally, and so notation that is sequential becomes very ill-adapted. And then, of course, there is, in some sense, directly connected to knot theory, as we already mentioned, but there are good examples of hierarchy relations between shapes that are hard to capture on a piece of paper, like the Borromean rings depicted here. Okay, so let's change gears and let's talk about musical improvisation. So the idea that I want to convey is that when I am improvising some music, or in fact, most people trying to play some music that is not written out, that is not fully rehearsed, you probably have some ideas running through your mind. I mean, there are times when you just let go and you just express whatever you're feeling, and you're in a sort of flow state that you're not really thinking. But most of the time, especially when you're practicing and when you're learning, you have some sort of mindset that you're trying to keep constantly, and you try to, at least the way I feel it is, I try to navigate a mindscape of possibilities, and I'm trying to make decisions on the fly. So currently, there are two extremes of notations that one can think of when doing music, especially on a keyboard, let's say for concreteness, like a piano or a harpsichord, an organ, or something like that. And one end is having a chordal structure. So this is something like a lead sheet where there's some basic rhythmic pattern, perhaps some guiding notes, and then mostly just chords. So this is indicating some general harmony that is to be played at certain rhythmic moments. Now, very similar to a lead sheet is a figured bass, which is standard in European classical music since the 16th century. And we find a very similar device here, where we encode harmonic information with a little bit more nuance, because now we don't just give general harmonies, but we actually give intervals, and we give bass notes. So there's a little bit more information than a lead sheet, but it's ultimately very similar. It is a rough skeleton of the harmony that is being played. Now, on the other end of the spectrum, we have a full score with gestures, dynamics, all kinds of notations and indications of what to do. And even perhaps more detailed would be a MIDI file containing all the waveforms and the spectra of all the sounds with all the exact timings and everything. So these are two ends of the spectrum. So one could argue that a very proficient musician maybe has something like a full score or a MIDI file active in their minds when they are improvising, but most reported improvisers experience tend to be more along the lines of, I'm thinking in terms of shapes, I'm thinking in terms of finger shapes and maybe some general patterns, but I'm not really thinking of every single note. On top of these two extremes of notation, there are what people identify as musical structures, things like scales or modes, the major, minor, all these sort of Greek inherited modes for European music or ragas for the classical Indian music. But then, of course, indeed, the cycle of fifths as a structural device that helps you navigate the possibilities when trying to improvise. So the point of this boundary of language, and why I'm mentioning musical improvisation as an example of a boundary of language, is that we have on one end the continuo style, chordal style notation. We have on the other end the score style or MIDI style notations, which are two different ends of the detailed spectrum. And so we are expecting that we would like to have also the structures that are useful, that inform the kind of, the color of sound and the kind of combinations and the different harmonies that we can do. And we want to perhaps find some middle ground that will be informed by these structures, like the cycle of fifths or the modes and the ragas, etc., but that will have a similar flavor to either a full score or a lead sheet. And that is not known. Some people have experimented. I am myself experimenting with examples like this, but still, there is no winning product out there to be used for that. And I think it's a good example of a boundary of, in this case, musical language. And then lastly, there is the problem of scientific measurement. And so one could simply sit down and ask, what is it really that we do when we measure anything in say, physical sciences? And it's not very hard to come to the conclusion that all we're really doing is measuring lengths and keeping counts. So we're somehow generally comparing the sizes of objects, and we are quantifying those comparisons. And we do so by keeping counts in particular, and we keep counts of many other things. And this is not necessarily just about length. We keep counts. It's something that we can do as individuals, but then we also build devices that keep track of the counts, either as mechanical devices or digital devices. And so this general perspective of the measurements in physical sciences can be seen as the metrological analog of space and time. Indeed, distances would correspond to space and time would correspond to counts. And it's interesting to think in these terms because, of course, all of physics has been thought, at least before quantum mechanics, has been thought to be some kind of space-time phenomena. And space-time was thought of as this sort of enveloping universe or enveloping space to all the phenomena. And it is perhaps not surprising that when one really goes down to the foundations of physical metrology or metrology in physical sciences, one finds the direct analogs of these concepts of space and time, so distance measurement and counts. So, of course, in other sciences, in social sciences or biological sciences, we don't have such a strict or such a direct conclusion in terms of what is it that we're measuring. Of course, if things get quantified and rigorously measured, they will pass by some physical measurement device, and then they will have these kind of limitations. But I want to make the point as a sort of an extortion of or a desire that the kind of incredibly complex and fantastically rich phenomena that we observe, for example, in the inner life of microbes and all the molecular machinery that we have now directly observed in that realm, or for example, the behavior of complex continuous media like fluids and turbulence and vortices and all kinds of very complex interactions, or indeed our civilization, complex societies and emergent behavior from loads of cognitive individuals that make up sort of a hyper-cognitive whole and things like that. So these are part of the world in the same way that a rod or light from a star or things like that are part of the world. And I just feel that we have inherited all this metrological paradigm that is essentially based on length comparison and keeping counts that is still to be developed into these higher realms. And this is not to say that we have to invent something that is completely different from what we had before. In fact, in some sense, those things that we developed will always have to be there, will have to be compatible with whatever else is developed. But I feel that there could be very reasonable possibilities of devices, or I don't want to say devices. It's not about the mechanics of it. It's more about the paradigm that is being understood to be operating with. And one, for example, can think that when we take a scientific measurement or a physical measurement, we normally measure some form of fraction, some rational number, some decimal with some accuracy or whatever, or at least a range of decimals or something like that. The question is, why is thought at that particular mathematical object? I mean, rational numbers are a specific mathematical object. There are many others, and it's a very direct question. One, if you're thinking more mathematically, more formally, can directly ask, what if we measured other mathematical objects, and we went around in nature, and we were sort of collecting other things than just rational numbers, right? So I leave that question open. I think it's a very enticing and a slightly psychedelic realm of thought, but I particularly enjoy it myself a lot. And with that, I just want to conclude by saying that, of course, there is always the looming threat of the ineffability monster, and I would say, do not fear the monster of ineffability, and always try to push the boundaries of language.